High above the Chilean desert, the domes of the Very Large Telescope stand guard over the cosmos. Inside one, an instrument called X-Shooter is about to make history. It's pointed at a tiny, faint object passing through our inner solar system, capturing its reflected light across an incredible range of colors, from ultraviolet to visible light and into the near-infrared. This single observation will give us one of the most complete spectral fingerprints ever recorded for an object of this kind, revealing the secrets of its surface chemistry. X-Shooter is a marvel of engineering. It's designed to split incoming starlight into 3 separate beams, each feeding into a different arm of the instrument. One arm captures ultraviolet and blue light, another handles visible light, and the third specializes in the near-infrared. Using special mirrors that divide the light with almost no loss, it sends each portion to its own detector, which is cooled to incredibly low temperatures. The result is a continuous, unbroken spectrum, a window into the object's soul, allowing astronomers to trace its chemical makeup in a single, powerful exposure. Before scientists can analyze the light from this distant visitor, a precise calibration dance begins. Arc lamps create a reference grid, defining the exact wavelengths of light. Special frames are taken to correct for any imperfections in the detector. Then, the telescope turns to a star that mimics our own sun, providing a baseline to measure the object's true reflectivity. Even our planet's atmosphere, which can distort the light, is carefully accounted for. This meticulous process ensures that what we see in the final spectrum is the object's real composition, not just instrumental noise or atmospheric interference. And what a spectrum it is. The data reveals a dramatic red slope, meaning the object reflects more red and infrared light than blue and green. This is a classic sign of complex, carbon-rich organic compounds on its surface. In fact, its color is among the reddest ever measured for any small body in our solar system. At the same time, the spectrum shows no clear signs of common rock-forming minerals, strengthening the case that its surface is dominated by ancient, carbon-based materials rather than crystalline silicates. When we look at the ultraviolet part of the spectrum, the story gets even more interesting. The object's reflectivity drops sharply, a feature that perfectly matches the light-absorbing properties of complex organic molecules called polycyclic aromatic hydrocarbons. These are the same kinds of materials, known as tholins, that scientists can create in a lab by zapping simple ices like nitrogen and methane with UV radiation. Finding this signature suggests the object S surface is coated in organic residues formed by eons of exposure to cosmic rays, long before it ever journeyed into our neighborhood. But while the surface tells a story of complex chemistry, the area around the object, its coma, is surprisingly quiet. There are no telltale flashes of gas emissions that we'd expect from an active comet. Instead, the faint glow surrounding the nucleus is just scattered sunlight bouncing off dust particles. This tells us that any volatile ices that once powered geyser-like jets have mostly disappeared. The object is now in a quiet, dust-dominated phase, its active cometary youth long behind it. Diving into the infrared data, we find more clues. There are faint hints of chemical bonds involving carbon-hydrogen and oxygen-hydrogen, but no strong signal of water ice. Beyond a certain wavelength, the reflected sunlight gives way to the object's own faint heat. By modeling this thermal glow, astronomers calculated a surface temperature of around 230 Kelvin, or minus 43 degrees Celsius. They also estimated its size at just under a kilometer across. Combined with its very low reflectivity, it's as dark as asphalt. We get a picture of a small, dark, carbon-rich body with very little activity. To figure out what the dust itself is made of, scientists turned to computer simulations. They found that the best way to reproduce the object's extreme red color and darkness was with tiny grains made of a silicate core wrapped in a mantle of organic material. These particles are incredibly small, about the size of particles in smoke. The models suggest that the surface is a mix of amorphous carbon and silicates, a composition very similar to dust streams left behind by other comets. It's a compelling match, reinforcing the idea that we're looking at a refractory, organic-rich surface. To be absolutely sure, astronomers cross-checked their findings with other powerful telescopes. The Hubble Space Telescope confirmed the object's reddish color. The James Webb Space Telescope extended the view deeper into the infrared, revealing the same continuum shape and faint signs of amorphous silicates. Observations from another observatory in Spain also agreed. When all these datasets from different telescopes are combined, they paint a single, coherent picture of an object dominated by complex organics and silicates, with almost no active ices. So, how does this object fit into the cosmic family? When we plot its color and brightness against all other known small bodies, it lands in a very exclusive neighborhood. It sits alongside the so-called D-type asteroids and the ultra-red objects from the cold, distant edges of our solar system. It even shares characteristics with the interstellar visitor Oumuamua. This suggests that despite coming from different places, these objects may have been shaped by similar processes. Long-term exposure to radiation that cooked their surfaces and drove off their most volatile ices. Models of the object's thermal history suggest that its surface has developed a crust of tough, refractory material, several centimeters thick. This layer acts like an insulator, trapping any remaining volatiles deep inside and preventing them from escaping. Any dust we see being ejected is likely lifted by gentler forces, like electrostatic charges. The fact that it still has a faint coma, even without gas activity, highlights how solar radiation pressure alone can mobilize dust from these ancient surfaces. Using advanced models, scientists were able to deduce the physical properties of the surface material itself. It's likely a porous, irregular regolith made of dark, carbon-rich particles. Light that hits this surface bounces around inside the particles before escaping, a process that naturally produces the red coloration and low reflectivity that we observe. This gives us a tangible feel for what it would be like to stand on this dark, alien landscape. Remarkably, these findings from a distant telescope echo what we've learned from missions that have actually visited comets. The Rosetta mission, which orbited Comet 67P, found a very similar mix of complex organics and silicates in the dust it collected. This powerful agreement shows that we can accurately determine the chemistry of these distant worlds just by carefully analyzing their light. X-Shooter's incredible range connects what we see from Earth with what we find up close, bridging the gap between remote observation and physical reality. Over several nights of observation, the object's spectrum remained remarkably stable. There was no flicker or change in its color that might suggest it was rotating, revealing different patches of material. This uniformity suggests the object is covered in a global blanket of processed organic material. If there were fresh patches of ice or rock, we would expect to see the spectrum change as the object spins. Its constancy is a strong sign of a surface that has been uniformly weathered over immense periods of time. Looking even deeper into the ultraviolet light, scientists were able to calculate an optical band gap for the surface material. This is a property of semiconductors, and the value they found is characteristic of something called hydrogenated amorphous carbon. This material is an intermediate step between pristine organic tholins and pure soot-like carbon. It's a quantitative signature that tells us the surface has been irradiated, but not completely burned to a crisp. This provides a direct, empirical link between the object and materials we can study in the lab. In the grand scheme of things, this kind of simultaneous, multi-wavelength spectroscopy is a game-changer. In the past, astronomers had to piece together data from different instruments taken at different times, introducing all sorts of uncertainties. X-Shooter captures the entire spectral portrait in a single moment, eliminating these issues. This leap forward allows for a much more precise understanding of an object's composition, from its electronic properties to its thermal glow. This dataset is now a benchmark for studying organic-rich surfaces everywhere. When we compare this object to other cosmic populations, dark asteroids, dormant comets, and even interstellar visitors, we see a shared heritage. They all tend to have reddish colors, low reflectivity, and carbon-rich surfaces. This suggests that the creation of complex organic molecules from simple ices under radiation is a universal process. It's a chemical pathway that likely operates in planetary systems throughout our galaxy, shaping the surfaces of small worlds everywhere. Ultimately, this incredible dataset provides more than just data. It tells a story of cosmic evolution. It traces the object's journey from a pristine, icy body to a radiation-baked, carbon-rich relic. Its red color is the signature of accumulated organics. Its dark surface is a record of its long exposure to the harsh environment of space, and its faint dust coma is the ghost of its once active past. Together, these features create a coherent, empirically grounded portrait of an evolved ancient body. In conclusion, this comprehensive observation has set a new standard for studying the solar system's most primitive and mysterious objects. The continuous spectrum captured by X-Shooter has provided a definitive look at a world defined by complex carbon chemistry, a radiation-processed surface, and a long, quiet history. Through meticulous calibration and modeling, a single stream of light has been transformed into a rich, scientific portrait. Revealing the life story of a distant called X-Shooter, astronomers captured a rainbow of light from this object, from ultraviolet all the way to near-infrared, all at once. This isn't just any pretty picture, it's a cosmic fingerprint, revealing the object's deepest secrets. And what a story it tells. The spectrum showed a distinct reddish color, getting redder as we move from visible light into the infrared. This isn't the kind of red you'd see on Mars. This is a special kind of red, the signature of complex, organic, carbon-rich materials. Think of it like a cosmic barbecue, where simple ices have been slowly cooked by billions of years of solar radiation, leaving behind a dark, sooty, organic crust. This reddish slope is a hallmark of certain types of asteroids, called D-types, and the nuclei of comets. These objects are thought to be some of the most primitive in our solar system. Ancient relics from the time the planets were just forming. They are time capsules, preserving the original building blocks of our cosmic neighborhood. What's fascinating is what the X-Shooter data didn't show. High-resolution scans revealed no signs of gas. Usually when a comet gets close to the sun, its ice turns to gas, creating a bright, glowing coma and a beautiful tail. But this object was quiet. It was surrounded by a faint cloud, but this cloud was made of dust, not gas. This suggests the object is either running out of fuel, like a dormant or exhausted comet, or its icy heart is buried deep beneath a thick, insulating blanket of this dark, organic dust. The incredibly low reflectivity, or albedo, of the object backs this up. It reflects only about 4% of the sunlight that hits it, making it darker than a lump of coal. This extreme darkness is caused by all that carbon-rich material, which has been weathered by space for eons. Scientists then turned to computer models to recreate the observed light. By simulating tiny dust grains made of a silicate core coated with a mantle of complex organics, think of them as microscopic, spacefaring M&Ms. They could perfectly match the reddish color. Their models suggest these grains are tiny, less than a micrometer across, and that the surface is covered in about 60% of this organic gunk. This is huge. It means that we can remotely identify the chemical makeup of these distant bodies. The ultraviolet light tells us about aromatic carbon compounds, the visible light reveals the size of the dust particles, and the near-infrared light searches for traces of water ice. In this case, there was almost no water ice on the surface, less than 3%. The original ices have likely sublimated away, leaving behind this refractory, carbon-rich residue. Based on all this evidence, the red color, the low albedo, the dust-only coma, and the lack of gas, the object is classified as a primitive, carbonaceous body. It's a lot like the mysterious interstellar visitors we've seen, like Oumuamua and Borisov, and dormant comets found in our own solar system. This suggests that the processes that create these organic-rich surfaces might be universal, happening in other star systems just as they do in our own. By capturing this complete, continuous spectrum in one go, the VLT and X-Shooter gave us an unprecedented, coherent snapshot of this object. It's like switching from a black-and-white photo to a full-color, high-definition movie. We're not just looking at a rock in space. We're reading a chapter from the early history of our solar system. These organic materials are the stuff of life, or at least its precursors. Understanding how they form and where they end up is a key part of the puzzle of how life might begin on a planet. Objects like this could have delivered these crucial ingredients to the early Earth. So, the next time you look up at the night sky, remember that it's filled with these dark, silent storytellers. And thanks to incredible technology and tireless research, we are finally learning to read their ancient tales written in the language of light. Thank you so much for joining me on this cosmic journey. If you enjoyed this and want to explore more wonders of the universe, make sure to hit that like button and subscribe for more deep dives into the cosmos. Let me know in the comments what you think. Could these objects have seeded life on Earth? Until next time, keep looking up.